Hello, everybody. This is Robert Graham on Network Password Hashes. Gosh, I can't speak already.
So today I'm going to talk about, first of all, about me. I do stuff. There's my GitHub account. So this slide presentation will be at the GitHub account later when I post it there. What I'm talking about today is, so we all know what this is, right? This is we're crashing, we get a password dump. It's like someone on the internet like hacks into a big website and dumps 1 million passwords, and they're like, maybe they're salted MD5 or something like that. So we go into OCL Hashcat or John the Ripper, and we go and we crack them, and we might choose, okay, this algorithm is salted MD5, so that's just the shorthand we use to refer to that. So what I'm talking about today is what we see on the network. We eavesdrop on the network and we get stuff, and it often looks like this. It's the same algorithm actually, and actually you could, in some cases, you can just go in there to the sniffed packets, pull out the fields, and pretend that they're a salted MD5 password, but in fact it's actually a challenge response. And then what you're looking for is to see that the challenge response matches the what you see in the packet. So most of what we talk about for password hacking is password dumps. We hack in, we download hashes, we run them through a GPU cracker like Hashcat. And what I'm talking about is we tap into the network, we dump packets to the disk or something, extract password hashes, and then we run them through a GPU password cracker. And this part, though, is the part that still needs to be done, is that we don't have a lot of algorithms in like OCL Hashcat or John the Ripper that can deal with the password hashes that we see on the network. And I'm going to go through that and show you what those algorithms look like. What I'm talking about is something like Wallow Sheep. Who does not know Wallow Sheep? So Wallow Sheep is this thing they do every year at DEF CON where they eavesdrop on the network and they disclose clear text passwords. So when people log on to like POP3 or FTP or Telnet and disclose in the clear without any encryption whatsoever their password, they pop them up on a screen at DEF CON. And it's really a lot of fun because you oftentimes see people there that are very well known in the community who have done something really stupid to disclose their password. So what I'm talking about here, though, is sort of a Wallow Sheep 2.0, where something similar might go on, where we look at the encrypted password exchanges, where the password's not in clear text, but which we can run through a password cracker and quickly get the original password. So you might find someone famous in the community who's very well known for security, but whose password turns out to be a very weak password and easily crackable. So when I log on to a computer, like my Gmail or a website or my chat session, how does that actually work? And there's 4 ways. One of which is the first one, which is the clear text one, where just you send the username and password in clear text, anyone eavesdropping on the network can then discover it, which is the Wallow Sheep way of doing things. Another one is where you encrypt the connection with SSL. And that's how we mostly log on today. If I log on to Twitter, it's clear text authentication, but it goes over an SSL connection so that no one can eavesdrop on that. Unless they, of course, hack the SSL connection, but that's really not what this talk is about on hacking SSL. The third way is crypto, where I do those challenge responses where I use crypto to hide the password so no one can see it without having to crack it. And that's what this talk is about. There's also a fourth way of doing it, which I'm going to talk about at the end. There are ways of exchanging passwords without using SSL, but in a way that can't be cracked either. So here's a typical password authentication algorithm. It's been around for decades. It's called CHAP. And CHAP means Challenge Response Protocol. And that's where you connect to a server. It sends you a string. You then hash that string with your password, send it back, the response back to the machine. And it's simply the MD5 of the challenge plus the password. And then the server then does the same calculation itself and compares whether those two are the same, and then lets you log in. And by hash, I often mean more than just MD5. Like there's the HMAC algorithm, which does multiple hashes in a complicated way to make cryptanalysis more difficult. But we're talking about password cracking, which is brute force or dictionary attacks, and we really don't care about the exact details of the protocol, the hashing algorithm. So whether it's using an HMAC, which is much more secure against cryptanalysis techniques, we don't care because we're never doing cryptanalysis. We're doing brute force password cracking. So here's an example. Here's the clear text way, first of all. This is POP3. It's a protocol that's older than many of us. Well, you guys, not me. And here's how I might log on. I might log on and say user Rob. Okay. Password. I choose a strong password there with random characters. And then it says, okay, you're logged on. You've got one message waiting. So POP3 supports a more secure method called APOP. And if the server supports that, the first OK message I get when I connect via the TCP connection, in those brackets, it puts a random string. And most of the time, that string consists of a timestamp followed by like their domain name, is the standard technique. And the timestamp's always increasing so that you can't replicate the same hash over and over. And when I log on now, I log on with my username again, APOP_Rob, but then I MD5 hash that challenge string plus my password, and then it allows me to log on. So that's how POP3 solved that problem. But for a lot of early internet protocols, they didn't really have any good solution for an encrypted connection. Oh, by the way, I want to mention this. So that's what this talk is about, is I can take that string, that challenge and response, the two parts that are in bold, and put those into a password cracker. I can pretend that one is the salt and one is the password. I can run it through Hashcat, and Hashcat can actually decrypt that. So that's how POP3, they add that APOP extension to it. But for a lot of early internet protocols, they don't really have any solution. Like SMTP didn't have any login because back when SMTP was created, there was no need to authenticate the user because you were exchanging email, and there wasn't the idea of a user that I cared about because, well, the email is just going to its final destination. And then spammers started exploiting servers that would forward email, and then people said, well, now we need user authentication to make sure you're allowed to use the email server. So what they came up with was a solution for all of these protocols, and that's called SASL. That stands for Simple Authentication Security Layer, but it's just this pluggable crypto system that plugged in to all these protocols. So whether you're using POP3 or IMAP or SMTP or LDAP or IRC or Jabber or even like VNC, SVN. VNC is a protocol for remote screen grabs. SVN does version control for source code. Jabber is a chat protocol. All these protocols now have SASL as one of their options. They also might have their own authentication techniques, but SASL is an option. And what SASL gives you is, not only does it plug into all these protocols, it allows crypto algorithms to be plugged in. So one algorithm is called anonymous, which just means no authentication. Another algorithm or two algorithms are plain and log in, which are both just clear text passwords. One puts both username and password on the same together, and the other one puts them on separate lines. They're just both plain text logins. And then the other algorithms on the next line are all these challenge response things, like the MD5 one. Like Digest MD5 is the same one, like APOP. NTLM is Microsoft's specific challenge response protocol, which we're going to talk about a lot more because it's everywhere in the Microsoft world. CRAM MD5 and SCRAM SHA-1 are variations on the same sort of theme of the challenge response with additional things. And the reason we need to have this is because these different algorithms impose different requirements on the server. So with Digest MD5, if I'm doing the calculation of the challenge plus the password, that means the server needs to store the clear text password, and that's a bad thing. As we all know, in the password cracking world, is servers should store passwords with assault. They should hash the passwords on the server, store it with assault, and use an algorithm like PBKDF2, which will rehash it like 1,000 times. And that's the secure way we know that passwords should be stored on servers. So that's what this scram SHA-1 or scram MD5 does. It's just the same challenge response password algorithm, but with the fact that you now are recognizing the fact that you're storing passwords correctly on the server. Now there's also a bunch of other things that we can't crack, like one-time passwords, where you have maybe a security token or something that tells what the current password is that will allow you to log on, and you can log on with that. And that I can grab via the network packets, but I can't crack it or do anything useful with it. SASL plugs into many protocols, and then there's this gssapi that also plugs into SASL. And the whole gssapi thing, we're going to see that in protocols, has its own plug-in architecture. So those are the main things we talk about SASL. So when I say, hey, I'm doing imap4, but I'm doing this scram SHA-1 login, or I'm doing VNC, and I'm doing digest MD5 login, or I'm doing SVN, but I'm just doing anonymous. That's how it's all these things would plug in to each other. So here's POP3 again, where I'm doing auth cram MD5 algorithm using the SASL technique. And it's a base 64 encoded string that the server gives me back, plus means it's something the server sends me. And it sends a challenge string that's encoded with base 64, and then I do my algorithm and everything, I send it back as another base 64 encoded string. What's in this string, by the way, is the username plus the response to the challenge. Or I might do auth cram SHA-1 instead of auth cram MD5, and again, it's the same thing. SHA-1's longer, so these strings are longer and stuff. Or I might be logging into a Microsoft Exchange server using POP3. And of course, Microsoft uses NTLM, which has a more complicated thing going back and forth, but doing the same logic. It's all encrypted. It's all encoded here in base 64 because NTLM is a binary thing, but POP3 is a text-based protocol, so it's all got to be encoded with base 64. We're going to see NTLM in other protocols, so we're going to don't really need to spend much time on exactly what's happening right here. If I were to base 64 decode that, that's what one of the strings looked like. I think this was like the initial login string that told it what user account it was before it got the first challenge back. So here's your Gmail login. So I connected telnetted yesterday to SMTP, or 2 days ago, smtp@gmail.com to port 587. So as we all know, SMTP normally runs over port 25. But there are these other ports that have been designed for things like users submitting email to the system. And so I telnetted to this port, and we see some interesting things here. So I say hello, foo, and then it comes back and tells me its capabilities. And so it's using SASL, so it tells me all the authentication techniques that it supports in SASL. It tells me I can do this login in plain, which are clear text, or it also supports its own custom extensions to SASL, its own plug-in protocol algorithms of just using OAuth or OAuth 2. And then I have no idea what plain client token is. These are all supported, by the way, because Google does this outsourced email system with Gmail. And you have this, who uses the outsourced Google Gmail at their corporate headquarters? Like Google Apps, yeah. So, so this whole system of Google Apps, and they have their own authentication. It all plugs in, and that's what all the OAuth and I suppose plain client token is for. So what I did was, okay, let's try the plain. So I did the login, which uses 2-string. So I tried to use that to log in, and it told me that no, I couldn't use that because I had to do the start TLS first. So it's got the plain text login, clear text login available, but only if I do TLS first, start an SSL connection. Yahoo does the same thing. Though it's interesting, it didn't advertise which authentication mechanisms it started. It just tells me you start TLS first. And the reason for that is that once you do the start TLS connection and do your SSL connection, you restart the entire process. So Yahoo only tells you which authentication techniques it supports only after that you've done the SSL. And then again, it'll give you, in this case, it's gssapi, digest55, or plain text login. So here's another example. In this case, it's imap4, another way of grabbing email from the server. And again, the server tells us, hey, I do a capability command, and it tells me, okay, here are my capabilities. For authentication, I support NTLM, gssapi, plain. And those are the 3 authentication techniques it supports. And then here's an example of doing just the authentication plain, and then it tells me, okay, I've logged in. So let's talk a moment about the scram technique, which is one of the ones that plugs into a lot of these protocols. So as I said before, just doing the raw challenge response with MD5 means the server has to know the password. With scram, the server doesn't. The server knows the password hash. It's been hashed 1,000 times with PBKDF2, and it has a salt. And so what scram does is it reports that. The client connects, and it says the user name is user in this case, which is kind of bad. I should put Rob here or something. And it gives a random string. And the server comes back and says, okay, I'm going to take the random string and add some more random characters to it. That will be the challenge. And by the way, the salt that adds this password is this salt string. And by the way, the iterations is 4,000 times rehashing the password. So that's what I've done to the password. But by the way, it's SHA-1. So now the server's told me how it stored the password in the database. So when I then do the calculation using the hash password, so what I do first is I take the password, I hash it with SHA-1, and then I do the rest of the calculations in order to then prove to the server that I know the password. So now with this transaction, I now can store the passwords correctly on the server and not the lame way with MD5. And here's how it might appear. So let's say I'm doing SMTP or Jabber for the chat protocol. And here's where I start. The client starts the connection. Again, these are the strings in scram to SHA-1, but these strings themselves, even though they include base64 encoding and they are text, they're base64 encoded again. That's because like a username might have like a UTF-8 password character in it that's binary, but the protocols can't support. So that's been base64 encoded again. So if we base64 decode this string from the Jabber protocol, it'll match this first string up here. So and by the way, Jabber is an XML protocol, so you can see how things like this plugin, the Sazzle plugin system works no matter what kind of protocol you have. In this case, it's XML, and it just plugs right into that. I have this twice here. I don't know why. Okay, so this is kind of hard to see. Hard to see on my screen, too. So this is an LDAP message. And this is LDAP login. And what we see here, actually, is... Who here knows Kerberos? Okay. So Kerberos was developed a long time ago by MIT. And the idea with Kerberos is you only log in once to a login server. And then from then on within an organization, that server controls your login to everything else. So that's why I had this other thing here. And that's what gssapi is designed for in the Sazzle system. Is that Kerberos plugs into that. But instead of the password exchanges, you get this ticket from the login server that allows you to log into everything else. So you arrive at work in the morning, you log on to the Microsoft Active Directory domain, and that's the Kerberos Exchange. And then when you log into your email, to the corporate website, to all this other stuff within the corporation, you're not actually ever giving your password ever again to these other servers. They never know your password. They just are granted tickets. So here's an LDAP exchange where I see up here with Wireshark, the first two packets were that Kerberos exchange of grabbing a ticket. And then here I see the LDAP protocol and just LDAP protocol decodes, and then blah, 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 blah. We see Sazzle. Sazzle says, okay, it's plug in for this thing. It's GSS API thing. And then within GSS, it's Kerberos, and it's just a ticket. So in this login, there's nothing here I can crack because these tickets are random strings. But in other cases, in similar sort of exchanges, what's going on there is something that I can crack into. So a lot of people know that Kerberos is this ticket granting system that you log in once and then tickets are sent back and forth to log into every other server in the corporation. But a lot of documents sort of skip how the Kerberos authentication works in the first place. When you're that first login, when you log into the Kerberos server. And the way it's done is it's not a password hashing system. Instead, the first step is I send my name to the server. And the server says, okay, I'm going to look up Rob in the database. Okay, Rob's password is blah. Or maybe Rob's password hash, and that's fine too. Like an NTLM hash. And then I'm going to use that password to encrypt the message back to Rob that has all that ticket information. So it's used for encryption. And then it sends back the message. Now, if I don't know the password, or if the server doesn't know the password, I can't interpret that message. I can't continue on with Kerberos. And this provides a mutual authentication technique because it proves to me that the server knows my password without me having to disclose to the server what my password is. So a lot of servers, you can set them up where whatever password exchange you send the server says okay because it doesn't actually know your password because it's not actually really the server you want to connect to, like hostile Wi-Fi access points. So that's how Kerberos works. And because this message that it sends back has a well-known format, it should be pretty easy to actually crack. And there's lots of different Kerberos supports plugins again. All these things support plugins. So the Kerberos authentication supports, for example, using MD5 to hash the password and then DES to encrypt the message. Or use SHA-1 to hash the password and use AES to encrypt the message. Or use MD4 to hash the password, which is what Microsoft uses already to hash the password, and then use like RC4 in order to encrypt the message. So Kerberos has a bunch of pluggable algorithms. But the upshot is that, well, we can't grab all the things like this that just pass the tickets around and crack those passwords. If we see the initial Kerberos exchange, we can use that for our cracking system. Here's the same sort of thing with Kerberos, but it's plugging into a different protocol here. So this is Microsoft's SMB protocol, the file sharing protocol. That's the main Microsoft protocol, port 445. And here we're logging into a file server. And again, we're seeing how SMB or an LDAP are completely different protocols. But once we get down to that plug-in for the Sazzle GSS API stuff, everything that happens after that point is all the same format. And this is something that's really useful for getting these things. If I wanted to write a program that automatically grabbed all this hashing information, I don't actually have to do as much work as I originally thought, because I only have to parse this once, write code for parsing this stuff once, and then I just need to figure out how to plug that into my SMB parser or my LDAP parser or my Jabber parser and so on. But okay, as I mentioned before, for the Kerberos stuff, we're skipping the login stuff. That was just the ticket granting stuff. But here's the same thing where I'm actually doing the login. Microsoft's primary login protocol, actually, that's used most of the time, isn't the Kerberos one, but is the NTLMSSP, which is one that's very well known. It's decades old by now. And And again, it just plugs into the same point. Here we're seeing the NTLM password hash, where it sends a random string as a challenge, and then the response is then the hashing of the password plus the challenge. Or in this case, they're hashing the password hash because Windows stores them as passwords as an MD4 hash. So that's a good discussion of what's going on for a lot of protocols. But there's a lot of other stuff that doesn't quite fit into that mold. Who here heard of the no IP incident of a few weeks ago? So Microsoft hijacked this company. This company was providing dynamic DNS, which means that your laptop, like if I were on the network right now, my laptop can go to no IP and say, hey, my current IP address for this domain name is this. And as my laptop moves around, people on the internet can still access my laptop via that domain name, even as my IP address changes. So dynamic DNS is used for home people whose providers change their IP address on a constant basis, and for things like mobile devices. So it's also used by botnets. So Microsoft hijacked that domain. They went to a court, they got a court order saying, give us that domain. And then, which is like a million, no IP had 1 million customers that now suddenly went from no IP and started pinging Microsoft to do all this dynamic DNS. And Microsoft servers fell down and all the customers were inconvenienced. That's kind of a bad thing. But, so I looked into how they do their authentication, how they do that dynamic, how my laptop would register a dynamic name. And I originally thought it was going to be via DNS. DNS has that dynamic DNS functionality built into it. And the way it works is you send a DNS query, and that query then contains a record. And I don't know how you guys can see, but this is a standard DNS packet. The last record in the DNS packet contains authentication. And the authentication simply takes the MD5 hash, which is used down here, of the contents of the packet plus the password. And again, it's a very simple MD5, straightforward authentication. So that's how I thought that no IP would work. And that poses a problem because Microsoft doesn't have any of those passwords, so it can't ever validate what those passwords are. So it has to then accept dynamic updates for anyone. So, by the way, in that DNS thing, again, that's pluggable crypto. So even though that was MD5 in that example, you can use SHA-1 and all those other things. Plus, then you've got this GSS thing again, which has its own pluggable system, which can then be all these other pluggable things like NTLM or Kerberos. So whenever we hit this password field, we constantly see that same pattern over and over, but there's this pluggable encryption or pluggable authentication system that matches something else I've already done. So that's what I thought that no IP was using. And as it turns out, it wasn't. When you install the no IP agent on your laptop, it sends queries so that when you change your IP address, it sends a query like this to the server. And we see here a get URL that contains this long base64 encoded string. So what's in that base64 encoded string? Clear text. So again, we're back to like this talk is supposed to be about cracking password hashes and robust authentication. But no, when we look into things often, we just see there's more clear text passwords. So yeah, so this was a real account I created, robbie.dns.net, that I created with no IP. And that was my real username and password that I chose. Because, of course, it's a demo. HTTP. So yeah, you think, well, isn't that over HTTPS? No, HTTP. So let's look at another case study. This is kind of interesting. Bitcoin, everyone knows Bitcoin. So one of the ways that Bitcoin system works is by Bitcoin mining. That's how transactions are verified and how new Bitcoins are created. So if I'm a Bitcoin miner, I'm going to have lots of working machines that are off just furiously mining Bitcoins. And I need to post my latest results back to a mining pool. These days, people don't mine Bitcoins themselves. Instead, they work with a pool that takes the collective effort of everyone together and then presents that as Bitcoin mining. That's because if you were to mine by yourself, it would take you 1,000 years to get 1 Bitcoin. So instead, you work with 12,000 people, and then it takes you only a month to get a partial Bitcoin. So here's what a miner might look like. So I've got a little mining account. The username I created is called Martin Woodford. It's got worker 1, the PR over here. And it's got an ASIC. An ASIC is a custom chip, and it's working away, generating 1/3 of a billion hashes per second. Bitcoin is also based on hashing. It's like password hashing, but it's slightly different. So he's furiously working away mining Bitcoins. He's mining at a rate of 223 nano Bitcoins per hour, which is not very much, actually. It's 223 billionths of Bitcoin per hour. And so I sniffed his connection. So how does he authenticate? And again, we see I think I've got the wrong string here. Yeah. So it was a similar transaction, if I had the right thing here. And I decoded it, and indeed it just showed Martin Woodford worker 1 and the password in clear text. Base64 encoded again, the same sort of thing, but in clear text. These Bitcoin miners support 2 different versions of the protocol. So that was the first version. The second version sends a JSON document, and just again shows just the username and the password in clear. One thing about this, though, is that that's not actually insecure. Because what these Bitcoin mining pools do is they have one username and password for your main account, and then assigns another username and password for each worker. So if a worker is compromised, it doesn't compromise your entire account. And if a worker is compromised, there's not much they can do with your account other than submit bad work jobs. Yeah. And most pools just don't even care. Yeah, all they care about is who do I give credit to. So even though it's clear text, it actually kind of works. Because no one knows what my main account name was. They only know the worker account name. And I mention this because that principle can actually apply to a lot of protocols. An example is SIP. SIP is the simple session, right? I'm trying to think, what does the I stand for? Oh yeah, I've already gone down the wrong direction. Yeah, session initiation protocol. And it for making phone calls across the internet, voice over IP phone calls. And all of our phones come with SIP. So if we're on an Android or an iPhone and someone gives us a SIP account, we can actually start dialing it without actually any special software on our phones. So SIP is a protocol that starts the session, and then RTP is the real-time protocol, I think, that carries the data, the voice. So SIP is only about starting the phone call. Other stuff handles the actual transmission of the voice. It's usually done over UDP, but it uses an HTTP-like protocol. So how does SIP authenticate itself? And again, it's got many of the same sort of plug-in stuff as the other protocols do. HTTP doesn't use SASL itself, but it effectively does use a lot of the same algorithms. So here we're seeing the standard HTTP protocol. It does, again, the MD5 exchange, where they send a challenge, which is the they call it NOT value, and then it sends back where it's hash the challenge plus the password. So the thing is, with SIP, if you're making a phone call over this public network here at the conference, I can grab your session initiation. Well, you register yourself. That's what this is up here. Is you're constantly, every few minutes, spitting out a packet to the SIP server. So if you're running a SIP on your phone, you're constantly talking to the network, giving up the password hash that I can then run through a cracker. And that's pretty dangerous. And I bring this up, that Bitcoin example, because SIP servers really should have that worker concept of where I've got one account, but the SIP information I put in here should be like per phone. So that the only thing you can do if you compromise this is compromise just my phone's connection to my SIP server, not my entire SIP account. So yeah, so phones should never require password. It should be something simple, like I log on to maybe an account, and it says, okay, your phone, I'm going to show you a QR code. And then you take a picture of that, and that's your authentication information for your phone. And by the way, it's going to be a completely randomized password, so that when they start cracking this, well, cracking happens because we're doing dictionary attacks. But if I assign a random, totally long random string to your phone, it'll never be crackable, and this will be perfectly safe. So let's talk about HTTP for a moment. HTTP supports authentication within the header. Most of the time these days when we log on to a server, we're logging on via stuff going within the URI or the post information that's then encrypted via SSL. Just via normal form. We don't ever use actual HTTP authentication. When we get those annoying pop-up box saying what the realm is, that's this authentication. It's useful mentioning this because there was that case with Weave, was the notorious internet troll broke into AT&T. I say broke into because AT&T had published the information of a bunch of all the early iPad account holders, publishing all their IP addresses on the internet. And in order to access that, you needed to set your script to have the user agent string say it was an iPad, and then anyone can access all of that account information. So that's not authentication. I want to repeat that because the lawyers and the judges and the juries think that, well, he had to change had to spoof his iPad user agent string, so therefore it must be some sort of authentication technique, but it's not. So what HTTP defines is this authentication header. And the way it works is you connect to a website with a URL, and it says you don't have access to it. And by the way, I support digest MD5 authentication. Your realm is this. The top of this is the realm information. It generates a random challenge string, and this extra string is verifying the account that the response matches the request. That's because HTTP is stateless, so they have to call it client rather than the server. So then you say, okay, my username is Sasa here. Example. You sent me this nonce. I was accessing this URL, and here's my response where I do the MD5 hash. So again, it's very crackable and stuff. And here's the exact algorithm of exactly what it's hashing. It's hashing the username plus the realm plus the password, and then hashing that value, and then hashing the other value here of the method, which is like get or post plus URL, hashing another value, and then hashing all this stuff with the challenge, and that's the response. So that's how it works for MD5 digest version. Here's the same sort of thing. Again, it's really small. Sorry about that. This case is using NTLM instead of MD5, and then we see here all the same NTLM stuff we saw before. That was in LDAP and SMB and all the other Microsoft protocols. Yeah, here's where I try to blow it up so you can see the challenge response. So this was the challenge it got from the server. It repeats back to the server, and then here's the hashing by password. And all the other information, like so on. So again, we see that there's the NTLM directly, but there's also the gssapi, where I can do things like Kerberos in there as well. And what's interesting about this, by the way, is the prevalence of Microsoft's techniques of NTLM and Microsoft's version of Kerberos. Because it's supported not only in Internet Explorer, as you expect, but also Chrome and Mozilla. And it's supported on the back end, like on Apache plugins and stuff. So this Microsoft way of authenticating things is pervasive. It's everywhere, even in Unix systems that you think are hostile to Microsoft. How many people here as organization, the Microsoft Active Directory domain is the central authentication for the whole network? So I find that odd because a lot of universities are very Unix-centric. But when you log on to your Solaris machine with your account, it's actually going through Active Directory to a Microsoft server. I find that really amusing because a lot of the students really hate Microsoft and love Unix, but they're still having to deal with Microsoft. Okay, let's talk about Microsoft some more. So Microsoft has this RPC, this remote communication technique called SOAP, where they send messages back and forth via XML messages. And SOAP supports SASL and their own authentication mechanisms. So all that plug-in stuff I talked about before also applies to this. And here's a SOAP request. It does stuff, and it's the whole XML stuff. And it gets done here. And so the password digest probably be MD5. And it'll see the challenge string that probably has to help it change. And here's the result. Again, for all the XML stuff that well applies to this. So we see in SOAP. And by the way, so when you're logging onto your Xbox system, this is the sort of authentication that's happening. So you're just logging onto your game, and it's actually what's going across is this sort of request. Though these days it's all been SSL encrypted now, so we can't see it anymore. But in theory, it's crackable if something happens with the SSL. Who here uses VNC? So, and often you might be using it and not really being aware, because like if you've got MacBooks and stuff, they use VNC for the remote screen grabbing. So VNC it's really old. It's almost 2 decades old. And over the years, it's had various authentication schemes. And eventually they got down to number 20 there, which is just that gssapi plugin. Rather than just the SASL plugin. So VNC supports SASL as well. It also has its own MD5 authentication, challenge response. It has the original authentication technique, which was this really lame thing, where it wasn't a username; it was just a password to log in. And again, you connect it to VNC. It sends a challenge, and you get a response, password, and then you logged in. Okay, so here's another protocol, OSPF. OSPF is the protocol that routers use to talk to each other. It's using MD5. MD5 is the password plus all the contents. Here is BGP. BGP is an interesting protocol. It's how all the backbone routers know about each other, know about the routes, and how to route packets and communicate the information to each other. There's no feature in BGP for authentication. So what they did was they added a feature, TCP. TCP supports options. So they added an MD5 option, TCP, to then encrypt all TCP packets, pretty much just for BGP. Let's talk about Radius. Radius is a server. When I log on to my access point, it then, in an enterprise, it forwards that login information to a Radius server. So the access point itself doesn't do the authentication. And it supports a bunch of techniques, including familiar ones. By the way, there's MSChatv2, which is easily hackable. The Moxie Marlspark now has a little hacking system just for MSChatv2 because it's easily hacked. But EAP is this plug-in system for that. And here's how it works. At my hotel, I stay at the Fedora. When I log on to the Ethernet there, I have to do AO2.11x authentication to the Ethernet. And it works. I send these packets back and forth to the switch, just raw Ethernet with no TCP or anything. And the switch sends me a challenge, and I send back a response. Typical challenge response technique. With MD5 again. But here's what the switch sends to the Radius server. It uses the Radius protocol over TCP or BGP in this case. A bunch of stuff, like timestamps, what my MAC address is, all this information, plus those same strings with challenge response. These are the same strings I had in the previous one. but it's now being packaged from the switch to the Radius server. So PPP is this old protocol that went over modems, and it has the same MD5 challenge response. Then they decided to put PPP over TCP, now it's a VPN technique, or PPP over Ethernet, which is now how you might log on to your ISP. And it has all these same challenge response algorithms, plus each of the plugin system. So VPNs are often very hackable. So if you're looking at a conference here, eavesdropping on people's protocols, you might find that people are establishing PPP, TP, and then they're using a challenge response which can be hacked fairly easily. Cracked, or the MSCAP v2, which is especially easy to crack. So now let's talk about World of Warcraft. How do they do authentication? Wouldn't that be great if people were playing World of Warcraft here at the conference that could hack into their accounts? Well, they use this lesser-known protocol called Secure Remote Password Protocol. And it's really kind of cool. It does the same Diffie-Hellman RSA exchange, where you generate primes, and then you exchange the primes by doing math. But it mixes in the password into this. And what's interesting about this exchange is that technically it's all in the clear. Nothing's being encrypted, so I can't see what's going on. But yet, because it's that public-private key exchange thing, I can't crack it. So it's not SSL encryption, though it's using similar algorithms with Diffie-Hellman. But it's in the clear, and I can't crack it, and I can't man in the middle of it. And this is actually what people everywhere should be using, something like this, and not all that crackable stuff. By the way, if you've got large capture files and you want to extract them, you can use T-Sharp. You can go get this presentation for the exact details on how to do that. Also, by the way, there's this program out there for Windows called KEnable, and it has a bunch of the cracking algorithms, and it supports a bunch of the protocols. So about a third of the protocols in my presentation it supports, and it will eavesdrop on the network, grab those hashes, and then it has its own little dictionary cracking stuff. It's really slow because it's not a GPU, but it's pretty useful. So that was what the talk was about. It's not about clear text or SSL or that SRP thing that World of Warcraft is using. It's about all these crypto exchanges and how they're just everywhere in the protocols we use. You eavesdrop on this network here. You get like a little wall of sheep thing going. We can grab so many people's hashes, run them through a cracker. If they're using weak passwords, you'll get their password. Any questions? Here's sort of a sample question, like what about what MySQL use? Well, they generally use plain text. So that's a sample question. I receive things. Question?
When you've got this universal plugin, thanks. When you've got this semi-universal shim like Sassel, how do you avoid, in order to provide that universality, how do you avoid having to store passwords in the clear on your server?
Well, that's the choice you have to make. It's often done with a configuration option, where you configure your backend server and say, I'm going to store these as hashed passwords, so therefore use scram and not MD5 authentication. So most of these services have that as a configuration option. If you say I want to support MD5 authentication, then it says, okay, now all your passwords need to be clear text. Okay, I guess that's it. I guess it's time for lunch.